we are going to start our paper 4 of semester 1 of this TYBSc class. So the paper 4, the course name is Group Theory. So there are 3 chapters in this course. So the chapter 1 is groups and subgroups. Chapter 2 is permutation. Permutations, cosets, and direct products. The last and third chapter is homomorphism. And factor groups. So we have to study all the 3 chapters. So group theory is the simplest mathematical structure, and it is the simplest mathematical structure, and the study of group theory is you can say a starting point of studying algebraic structures. So let us start our first chapter, groups and subgroups. So first chapter, groups and subgroups. So before going to group, we need, or we can say, we require some basic knowledge of sets, because all we are doing with this group is absolutely with the sets. So absolutely we have to define some functions, we have to define some operations on the sets. So the same concept of set can be extended to group. So let us recall some definitions. So basically, what is meant by a set? So all we know is a set is a well-defined collection of objects. So what are the terms there? A set is a well-defined collection of objects. So what we call object that should be collected in which manner? A well-defined manner. So the collection means generally we use the word collection. So the collection is nothing but aggregate of things, right? So well-defined collection of objects. So what is meant by a well-defined object? That means a very simple thing, there should not be any ambiguity whether the object belongs to the set or does not belong to the set. So for example, suppose I choose S to be X, Y, Z. So these X, Y, Z are 3 objects, and I have included them into a set X, what I call the set X. So what is the well-definedness of these objects X, Y, Z? So it means what we call an object in a set is an element of the set. So if X, Y, Z, these are 3 objects in this set S, so we can call them as element. So we can say that X, xyz belongs to set S. So what is meant by well-definedness? So there should not be any ambiguity. That means whether the object definitely belongs to S or definitely does not belong to S. There should not be ambiguity means what? The object will definitely belongs to set S or definitely does not belongs to set S. So there should not be any confusion whether it belongs to set or does not belongs to. Right? So it should be a clear thing so that it has to be either in set or it does not have to be there. Right? So it is a well-defined collection of object, a set. So you have studied, you may know some concepts of union of two sets, intersection of two sets, empty set, and then subset, superset, power set of a set, right? So and then we have studied, you know, we are all familiar with a set of numbers. In fact, we have used somewhere set of numbers. Which are these sets? Which set of numbers we have studied? Z, set of integers. R, set of real numbers. Q, set of rational numbers. C, set of complex numbers. What are the set of other set of numbers? So I can write them as Z plus. So set of positive members of Z. So set of positive integers. Similarly, I can have R plus, set of positive members of respectively of R. Similarly, I can have Q plus. So I can say that it can be a set of positive members or positive elements of set of rationals. Also, I am giving because we have to use all these notations, all these set of numbers. Z star. So I can say it as a set of non-zero members or elements of set of integers. So similarly, I can define R star to be set of non-zero members of R. Similarly, I can define Q star to be set of non-zero members of Q, or then C star to be again a set of non-zero elements or non-zero members of C. Okay. Now let us see the cardinality. All you know what is meant by cardinality of a set. Cardinality. So let S be a set. Then what is meant by a cardinality of a set? Then a cardinality of set S is the number of elements in S. Right? We denote cardinality of S to be by this way, the number of elements in set S. Then you may remember the Cartesian product. Cartesian product. So suppose I have two sets. Let x, y be two sets. Then the Cartesian product. Then the Cartesian product x cross y will be collection of elements. Which elements? Collection of ordered pair x comma y such that the first member x is from first set x and the second member y is from second set y. So the Cartesian product is collection of such kind of elements x comma y, so that the first member x is from first set and the second member y is from second set y. So x cross y, the Cartesian product of x and y, will be the collection of such kind of elements. So we have seen the cardinality. So what can be the cardinality of this Cartesian product? So let cardinality of x is m. So there are m elements in the set x. Cardinality of y is n. There are n elements in the set y. So how many elements would be there in the Cartesian product of x and y? So then cardinality of x cross y would be the cardinality of the Cartesian product, the element of this kind, collection of this kind, x comma y, so that first member is from first set, second member is from second set, and we want cardinality of this set, this collection. So it has to be m into n, where is m and n are natural numbers. Okay? So now we know the relation. What is meant by a relation? Now let us define a relation. So a relation between x and y, between the sets x and y, is subset of the Cartesian product x cross y. You might have studied the types of relation, which is a reflexive relation, symmetric relation, and transitive relation, and then equivalence relation. So all these relations are subsets of the Cartesian product, because the Cartesian product takes all types of ordered pairs, so that first element is from first set, second element is from second set. Now let us define a function which is also a subset of, it is some kind of relation, so it is also a subset of Cartesian product, because from first year, second year, you have studied this definition of function, and you see that the graph of function is subset of domain, Cartesian product of domain and codomain, right? So you might have seen it that this function from set A to set B, then the graph of f was subset of the Cartesian product A cross B, right? So something like that. So the definition of function: a function phi mapping x onto y, so x into y, is a relation between x and y, is a relation between x and y. With some criteria. What is the criteria? With the property that each x in x that appears as a first member of exactly one ordered pair x comma y in phi. So phi is a relation, a function phi which is mapping x into y is a relation between set x and y with property. Which property? For each x belongs to x, which appears as the first member of exactly one order pair in relation phi. So phi is relation between x and y. So which has to be as it is a relation which has to be subset of x cross y. Right? So it is a relation, but with some restriction. What restriction is there? For each x in x that appears, each x in x, which will be, if it is element of x, so it will be first member of the order pairs. However, how many times it appears? This much times. As first member of, but it should appear as first member for exactly one order pair. Means what? The definition of function is exactly same as the definition you have studied earlier. What is the definition of function? F is function from x to y. If for each x belongs to x, there is unique y in y, so that we will get y is equal to f of x. Y is image of x under function f. Right? So it is the same thing. We are collecting the order pairs x comma y, means what? X is input, y is output, x is from domain, y is from codomain. So we are making such kind of order pairs so that x is from domain and y is from codomain. So what we want by definition of function? For each x in x, we want unique output y. So for each x in x, we want unique output, unique image in the codomain. So if we come here, it means we are making the order pairs with the element from domain and element from codomain. So what we want? Unique output to each element of x. So means the element x when appearing as first element of the order pair. So such order pair should be exactly one. Right? So if x has image y, so there should not be any order pair with x having image y dash. Right? So such case should not be there. We cannot call it as a function then. Okay? So this is the definition of function. Then you might have studied the definition of one-to-one function. This is one-to-one function. The function or mapping. Okay, let me. So if this is the function, so what will have? X will be domain of the function. Domain of phi will be x. Codomain of phi will be y. And what will be the range of phi? So it will be image set of phi. That means image set will collect all the images phi of x such that x is element of x. Right? Now, one-to-one function. So what will be a one-to-one function? A function phi from x to y is an into map then phi is 1 to 1 if phi of x1 is equal to phi of x2 only when x1 is equal to x2 when these x1 and x2 are from the domain. So it means that if the images are same, the function is 1 to 1. If the images are same, then their pre-images, the elements from the domain, has to be same. And the other definition for this 1 to 1 function you can have in some other books. It will be a negation of this statement. That means phi from x to y is 1 to 1 if x1 not equal to x2, then phi of x1 not equal to phi of x2. That means if the elements in the domain are distinct, then the images in the codomain are also distinct. That means what? Distinct element in the domain maps to distinct elements in the codomain. So 1 to 1. So this into map is 1 to 1 map. Then onto function. So what would be onto function? Onto function. And into map a function phi from x to y is onto if range of phi is equal to 1. If range of phi is equal to the codomain. That means all the elements in the codomain are exhausted. Every element in the codomain is image of some element from the domain, right? Then one-to-one correspondence. So a map phi from x to y or let us say two sets x and y have a one-to-one correspondence. If a into map phi is 1 to 1 and onto map. So Now let us define the same cardinality of two sets. So two sets x, y have same cardinality. If the number of elements in x same as number of elements in y. By other way, we can say that is if there is a one-to-one correspondence between x and y. One-to-one correspondence between x and y. That means one-to-one and onto map. The next thing is disjoint set. So when the two sets are disjoint, we have studied this earlier. If any two sets do not have any element in common, then they are disjoint. So the sets are disjoint. The sets are disjoint if any two of them have no element in common. Right? And then partition. The definition is a partition of a set S is a collection of non-empty subsets. The partition of a set S is a collection of non-empty subsets of S such that each x in S is in exactly one of the subset. Okay? So if this is the set S, so it is collection of subsets of S. So what I'll get? I'll get this kind of partition of S. Each partition is collection of subsets of S. And the subsets are called sets. This collection of subsets. So this is one cell of the partition. Now let us go to the chapter 1, which is group and subgroup.